So, in our last day lecture, we have discussed about energy and co-energy and also the calculation of stored energy in an electromagnetic system. However, there we means before I could discuss another example due to some unavoidable circumstances, I need to take break. So today I'm going to discuss that. Here we are having the same example like the previous one. Only thing here is that unlike the previous one, if we go back to the previous one, you can relate also that here you can see that current was constant, I is equal to 10 ampere. However, here the current is means function of your plunger position. This is let me quickly explain this dynamics of the system. Here it is the same magnetic core. This one is connected with the source, and this coil is drawing current I from the source. The flux linkage is lambda. We are assuming it as a lossless intern coil. So lossless intern coil means even if you have some resistance, we are considering that resistance is lumped outside that coil and the coil is lossless and it is also not undergoing any kind of hysteresis or eddy current losses. Because if you consider hysteresis and eddy current losses, they are you can consider them as a leakage to your magnetic reservoir, magnetic energy reservoir, because the purpose of though means, or better to say that their introduction in your circuit will always cause what, will always cause heating of your iron core. So whenever heating means, you can consider that whatever amount of energy you put in your magnetic reservoir, some amount of energy is getting wasted by means of means that is converted into thermal energy. From magnetic energy it is converted into thermal energy. While in case of uh, a, your induction cooktop, what we do, we intentionally utilize that principle to convert magnetic energy in thermal energy. But in case of a transformer or in any other devices, it is not desirable that it is getting converted into thermal energy. So that is the issue here. But while we are considering this discussion, we are considering that as if hysteresis loss and net current loss is not present and these losses are negligible, right? So if that is the case, now you can think that here it is drawing a current Ix, where this X previously I was 10 ampere, however here it is a position of this plunger, and that is quite logical to take this assumption, because you can understand, or if you apply your common sense, whatever we have discussed so far on magnetic circuit, magnetic material, there were a lot of discussion during transformer analysis also, in YouTube videos as well as in our class. What you will be able to figure out that if we move this plunger away, like here, then what would happen? If it is D, then you can understand that the amount of EMF that must be produced by the coil will be very high, because your this is actually a series circuit, and when this plunger is absent or it's not in this gap, then your EMF has to overcome in order to produce a certain flux. Your EMF has to overcome this path, air gap path of high reluctance. So like in case of a transformer, if we insert a cut at its core, then what it will how it would affect the transformer performance? It will draw more magnetizing current. Similarly, here also in case of your means system, if this plunger is outside, it will draw a heavy magnetizing current, and as you allow this plunger, obviously your only current will be magnetizing current. You can consider it as a primary of your transformer, while the secondary is not connected or secondary is open circuited, because whenever your transformer secondary is not connected, you can drop them. There is no means purpose of considering or disregarding that one. So here it is like you are having, this is your transformer primary, and here you are means having this movable plunger. So you can understand that when that this plunger is in this gap, then the amount of current, and when it is not in this gap, what would happen to the amount of magnetizing current. Now we can write it in this formula. So what is our objective? Our objective is to find out the force experienced by this plunger. So what we can write here, we can write that like if you write the Lx, right? So what is Lx? Sorry. Lx is equal to what? As we know, it is mu 0 n square d 1 minus x by d divided by 2g, where g is the air gap. And this formula we have already discussed in our previous session. Now we are assuming that this system is a magnetically linear system, and for which we can calculate the force like for which we can calculate the force like if LD is equal to I square by 2 so it is giving us if you do ddx of this, what you will get, alright. However, here your current is not constant, your current is also a function of x. So if you replace that current with this function, what you will be getting here, you will be getting right. So what about the co-energy of this system? This is the force. Now let us calculate the co-energy of the system. As it is a linear system, what we can conclude about the energy relation and co-energy, it will be equal to each other. So in that case, co-energy expression, what you will get will be, just a minute, let me clean it first. Just a minute. So the expression will be very similar to the energy. Only thing is that in co-energy, what is we consider, in energy it is the flux linkage and the position, while in case of co-energy it is our current and position. So what it would be, that is I square by 2 Lx, and you will get now you can further substitute this I square, like you will get, it will be, there is no minus in co-energy, then you will get, it will become I naught square n square mu 0 LD 1 minus x d, then x by d whole square into 4g, right? So this is the whole thing, this is the expression of our co-energy. Now we can proceed with that, like for our next example. So here in this example, it is, we have to, this is a structure, a magnetic circuit, where I have like the first part I am taking all these examples from the book of Fitzgerald. So with an expression for this inductance of magnetic circuit, here we can express it as a function of the rotor angle. Had we considered a rotor that is purely cylindrical in nature, then the system inductance will become means independent of rotor angle. However, here as the rotor is salient, not cylindrical, therefore rotor angle make a huge contribution in that magnetic circuit. It can alter it in a significant way. Why? Because when you can understand the rotor axis is aligned with this shoe, then the air gap experienced by the magnetic flux, and when it is perpendicular, rotor axis is perpendicular to your magnetic shoe's axis, then the air gap is completely two different air gap, and there is a significant difference exists between these two air gap, and that may cause significant alteration in your magnetic circuit. Now see here what is happening, that it is made up of, as I said, it's made up of high permeability material. Now here one thing is clear, that when the rotor is in means perfectly aligned, rotor axis is aligned with the magnetic shoe axis, then there is two air gap, each of them of having length g, right? So that and the two air gap are in series. So what we can say that air gap magnetic field intensity, that is HAG, is equal to Ni by 2G. So we are assuming that uh, permeability of this structure is means infinite. Now this high electric steel, as they have mentioned, now this steel must remain finite. So if you want to make this means flux density inside this steel remain finite, then what is the nature that we can say that each steel, that is equal to be still by mu. Actually this mu comprises mu and mu r, both of them. So the co-energy density, what is the formula for that co-energy density is that co-energy density formula is right. So this is the formula for co-energy density, and from this what you can see that basically what we were talking about, that energy, we can find out the accumulation of energy across the air gap. So same thing we can show for the co-energy. Now that, and also for their density too, like where the energy density is high, there also the co-energy density is also high. So co-energy density in that air gap, what would be the value of co-energy density in the air gap? It is mu naught H Ag square by 2. We are getting this from this formula. Now the now here one thing is very means somewhat complicated, that we need to find out the volume of two overlapping air gap, and the volume of two overlapping air gap, how to calculate. Like here it is R1, then we must also know the like axial length is H here, and it is that like sorry, axial length is that length perpendicular to the page H. Okay, so if we means this structure is like the length H is perpendicular to the page, so you can consider the thickness of this structure is small h. Now see that air gap is G, so the volume of these two overlapping air gaps is how much? It is 2GH R1 plus 0.5 Actually, this empirical formula is coming out by solving or finding out the geometric symmetry between the structure and also application of some means geometrical identities and concepts. However, this is not very important to us that what is the empirical formula here I have written. I just taken it from the book of Fiedler. But what is important to note that how this volume of air gap is also depending on the function of theta. So when theta is say 90 degree, then you can get some value of this air gap, while theta is small or 0, then you can get some other value of air gap. So this is very interesting to note that this is the overlapping air gap. So what would be the like the co-energy will be what? Co-energy will be the air gap co-energy density, which we have already found out, that is mu 0 h ag square by 2 with this overlapping air gap volume. Then this will give us the expression of co-energy. Then the expression of co-energy is like it's a complicated equation. Let me write it. So this co-energy will be how much? This is our, where is that cursor? See, just a minute. There is some problem. So here you will get that expression by this is our air gap, this is density, co-energy density, and this one is volume. So if we multiply them, two of them will result in what? They will result in mu naught h a g square by 2 into 2 gh r1 plus 0.5 g theta, right? So if you form that, then what you will be getting? You will be getting, it will give you an expression mu 0 ni whole square h r1 plus 0.5 g theta, sorry, r1 point, sorry, divided by 4g, right? Sorry, here I have missed this 2g. Sorry. Just a minute. Made a mistake. However, what is HAG? HAG is Ni by 2G. So here when we put Ni square, one more expression will come here, that is by 4G square. So in denominator you will have 8G square and in numerator you have 2G. So 8G square and 2G, if you do further simplification you will get 4G in the denominator, right? Now this is the whole thing. After that, what we can find it out more, like we can find out the expression of torque. The expression of torque is what it is. Now see this expression of torque. One interesting thing here we'll be able to observe. So after doing this, what you will be able to observe, you will observe that this is equal to now the sign of this torque is positive, so it is acting in the direction to increase this overlap angle theta, right? And thus it means it is very common that it is trying to align the rotor in line with the stator, means this iron structure, this shoe-shaped structure pole face. It always try to minimize the air gap, and that is quite logical. Why? Because even if you try to analyze this from the perspective or from the in the context of energy conservation, then you will see that energy always try to maintain the minimum energy state. Means the nature, not energy, rather the nature wants to maintain the minimum energy state. So when your rotor is aligned with your means stator shoes, then what you will have minimum amount of air gap, and minimum air gap means minimum air gap energy. And we have already discussed and established that whatever energy is stored in this magnetic reservoir, that is across the air gap. So if we can reduce that air gap, obviously that air gap reduction of air gap will reduce the amount of energy stored in the system, and that is a natural choice for most of the system. They want to reduce the amount of energy stored in them. Now you can put the numerical values to further figure out the amount of torque, like what is that pin? Yeah. You will get what is your now for BAG, it is given 1.65 Tesla. So if it is 1.65 Tesla and you know U naught is 4 pi into 10 to the power minus 7, you can figure it out. It will give you 1.31 into 10 to the power 6 ampere per meter. So it's a very high value we are getting here. Now Ni is equal to how much? Ni is equal to 2G into this HAG. So what about this 2G? It is 2. G is 3 millimeters. So 2 into 3 into 10 to the power minus 3, because we are doing everything in scalar, in SI unit. So it will give you 7860 ampere turns, right? And for that 7860 ampere turns, what we will get, that the torque let me write the formula: mu 0 n I square h r1 plus 0.5 g by 2g. So we know all the values: mu 0 ni r1 g, everything is given to us, and as 8. So this will result in, okay, so it's producing a huge amount of torque. Now we'll move towards the multiply excited energy system. So what is there in multiply excited energy system? Your DC machine is an example of multiply, DC motors particularly is an example of multiply excited energy storing system, where you are giving your supply to your field as well as to your armature, and you are getting, I am talking about obviously separately excited machine. So this and not only this separately excited DC machine, we can have also our synchronous machine. Synchronous motor always work in this way, and in some control our slip ring induction motor also work as a multiply excited magnetic field system. What is we are having here? We are having two different energy source, two different current, and two different flux linkages, right? So here what is important, what I was talking about, that in many machines we can find it out that we are having two different excitation. Now here one thing is, if you have observed, here we are considering that we are having only one output. It may so happen that we can have many output also, but for that sake of simplicity we are considering we are having only one output. Like you are putting energy to your magnetic reservoir using two input channels, namely lambda 1 I1 and lambda 2 I2, and you are having only one output channel, right? Now this one, we can see that if we consider it is representing a rotary motion, just like the previous example, where means this one was not excited, but we can also put some wire on this structure and we can have a doubly or multiply excited system, right? So here in this case, if we consider a rotary system that is having torque T field and the position theta, Then what we can write the fluxes for the differential energy dw field. Obviously that will be function of a function of lambda 1 lambda 2 theta, and if we consider the co-energy it will be a function of I1 I2 and theta. So what you will get here, it will be okay. And in the direct analogy of with previously discussed single element system, what we can write here, we can write that this is our total expression of energy. So what we can write, we can write uh, I1 is equal to delta W field by delta lambda 1. Actually it is a function of three elements, so lambda 1, lambda 2, lambda 3, I am writing that, while keeping lambda 2 and theta constant. Similarly I2 can be found out like d W field by delta lambda 2 keeping lambda 1 and theta constant. Similarly our torque, not theta, torque can be found out by doing del W field del theta while keeping lambda 1 and lambda 2 constant. So here you get the essence of taking partial derivatives. Okay, sorry. Obviously it must be negative. Why? Try to understand one simple thing, that why all the time force or torque is having a negative relation with your stored energy. Intuitively we can answer this, like if we increase the stored energy, obviously like if you want to increase your bank balance, then obviously you have to either you have to means increase your income, or you have to curtail your means expenditure. So if we try to have a relation between bank balance and uh, expenditure while keeping the income constant, then obviously they will be means they will vary in opposition. Like if your expenditure increase, then obviously your bank balance will decrease. And the same thing is true for that torque or force with stored energy, stored magnetic energy. That is why all the time we need to incorporate that negative sign to ensure we do not means, or we rather we corroborate with the understanding of energy conservation, right? If we do not want to corroborate with the energy conservation, then what we need to do, we can drop this negative sign, and then it will indicate that if you means produce more output from your system or extract more output from your system in form of mechanical energy, your magnetic energy reservoir energy will also rise. But that is not the case. Obviously if you try to extract energy from that system, obviously your magnetic reservoir energy will decrease with that increase of your or rising value of your energy that you are drawing from your output terminal, right? So one thing here, like that single system is singly excited system, it was easy to find out the energy, and but still what we could do there, if you remember, we considered them as state variable and did pathwise integration, right? So for single excited system, we considered it was like we are having two variables, x and your lambda, and along, as we are again we have to consider that it is a lossless and totally conservative system, because if you consider a system that is not conservative in nature, then obviously your means energy expenditure or whatever will become a function of the path chosen by you. But for a lossless system or a conservative system, it is only the terminal points that determine the energy, not the path that you have chosen to reach from point 1 to point 2. So here it was two-dimensional case. Similarly, here we will do the same thing for three-dimensional case. Like here, when we are having multiple energy, we can just, instead of considering a two-dimensional case, now we'll move to three-dimensional. And when we need to means find out the energy expression by integration, then we can carry out that integration along the axis, right? So, so you can see here for magnetically linear system, lambda 1 is this much, lambda 2 is this. So we are having I1, I2 we get from this value. Now with this we can find out the total energy stored in our system, and that expression of total energy is this, right? Now one thing you must notice that here the torque is dependent on, means you have to keep lambda 1 lambda 2 constant, and that is quite obvious. Why? Because in case of say, if you consider the case of separately excited DC machine, you can easily understand this. Like if you weaken your field current, or if you either reduce the current that is flowing through your armature, in both the cases the torque produced by that swing will be reduced. Why? Because the source of energy or the mechanism of carrying energy into your magnetic reservoir is the two currents that are flowing from your armature voltage source that is connected across armature, and the another voltage source that is connected across field winding. Basically, the DC separately excited DC machine absorbs energy from them, and then it store it in magnetic reservoir, and some part of it is getting transmitted to you by, or means converted in mechanical energy and transmitted to you by the motor shaft. So that is the case here. Now here also we can define the co-energy function like the previous case, and the advantage of defining co-energy function is that all the time you cannot have direct access to your flux linkage lambda 1 lambda 2. So in that case, if you have the expression of your co-energy, then it will be helpful. Actually this discussion is just like the single excited system. Only thing is that here we are having instead of one energy source, we are having two energy source. So how can we define the co-energy? That like for normal co-energy system, we can define it like, let me write it here. The co-energy will be this is the total energy, right? Means total energy absorbed from input. So this is the expression of co-energy. Now here if you do this, then you will find that the expression of torque is positive with respect to co-energy. Obviously, if you can somehow reduce your bank balance, you will have more money to spend. So that is the simple thing. If you reduce your energy stored in the magnetic circuit, then you will get more energy to develop more torque, and that is the case here. And similar to the previous case, here also you will get the expression of, like, you can find out your lambda 1, lambda 2 by doing this. So in this way you can do, and eventually you can means get this expression, that is the expression of torque based on this co-energy. So in case of means this is a metric representation. I am not going to that because metric representation means may make you confused, because I am not sure how many of you still remember the matrix manipulation technique. So what I need to go, or rather we need to consider, is the second example. This is the example here. Basically this actually mimics the operation of, sorry, this system mimics the operation of your salient pole synchronous machine. So in case of salient pole synchronous machine, what we have, it is like we are rotor and stator both are energized. Now in stator we are having one winding, and one thing you must note that the stator, rotor, all these are having, if you see that the direct inductance, that is a function of cos 2 theta, while the mutual is a function of cos theta only. We'll discuss more on this when we will consider the machine representation as a matrix in your next semester. That will be there, that how we can represent or consider a machine acting during its linear operation as a matrix, because matrix manipulation gives us some added advantage over normal representation. So here instead of means discussing on that why it is 2 theta and why it is theta only, in next semester also you will get ample and scope to study all this. So what we do, or what is we are interested, we need to find out the plot of torque for two different current. Now here what you will be observing, that due to the expression of your, yes, this is the reason why. Let me write the expression of torque first. So torque is how much? It is like I1 square dL1 theta d theta one thing I would like to hear from you, why here we can replace the partial differentiation by ordinary differentiation. That is also an interesting thing to note. So if you do that, then you will get the value of torque. How this is, we are getting this value, like this, if you consider them, then your total energy or co-energy is how much? Like co-energy is what is your co-energy, that is lambda 1 I1 minus lambda 2 I, sorry, plus lambda 2 I2 minus your energy. And what was your energy? Your energy is something, so if from that formula we can get this one. The interesting thing here is that expression of torque is given. Just let me clear this board once. Here you can see that this torque, there are two parts. This one is very important and interesting. This is the phenomena of operation of reluctance motor, that is also a case of salient pole synchronous machine. But even if you do not uh, provide any excitation to this, due to this saliency, it will execute or give you a torque. Another torque is due to this mutual action, and you will get means your torque will have two components. One is varying with theta, the rotor angular position. Another one is varying with 2 theta. The 2 theta component of the torque is actually the reluctant torque. And even if your rotor or here this circuit is not energized, still it will play the role because of the saliency or unevenness in the circuit. But if you consider the main torque, that is due to the mutual interaction of your stator and rotor torque, here due to these two, then you will see that this will depend on what? This will depend on this, sorry, L12, right? So this will depend on L12, and you can see that I am trying to give you an intuitive explanation. L12 is a function of theta. So here the mutual torque is varying with theta. However, the salient torque, that only depend on the inductance that are due to the structural, had we considered complete means circle, then what will have a different expression of torque, and there will be no theta present in our expression. So in that way, what you will get the total torque, that is not sinusoidal, a non-sinusoidal periodic curve you will get, right? So in my next class I would like to start that, or in my next lecture I would like to start fundamental of rotating machine. So in that fundamental of rotating machine we will discuss the other topics. Actually I initially I planned for covering up the basic state space representation of machine, and also how to use finite element method to do flux calculation, but giving the time constraint, I would like to curtail the amount of time will be assigning to this particular topic, and we should jump to that fundamentals of rotating machine. Sorry.